Giant ships navigating vast oceans often leave us in awe and wonder. How can these massive steel structures, weighing hundreds of thousands of tons, float while smaller objects like stones or metals sink when dropped into the sea? Is there a secret in the design and construction of ships that allows them to stay balanced and upright even in the face of strong waves and winds? Large ships can stay afloat thanks to Archimedes' principle of buoyancy. Any object submerged in fluid experiences an upward force equal to the weight of the fluid displaced. If this buoyant force is greater than the gravitational force pulling the object down, the object will float. The design of ships ensures that most of their volume is filled with air, making the weight of the displaced water greater than the weight of the ship itself. The balance between buoyant force and gravity keeps the ship stable and prevents it from sinking, even when facing challenges at sea. To illustrate buoyancy, consider a simple experiment. If you drop a stone from a height onto the ground, it falls quickly due to gravity. However, if you place the same stone in a container of water at the same height, it takes longer to reach the bottom. The resistance the stone experiences is the buoyant force slowing its descent. How is this principle applied to ships? Ships are larger steel vessels weighing hundreds of thousands of tons. However, it's not just the material that makes them float. The shape and content of the ship also plays a role. Ships are not solid blocks of steel. Instead, they are hollow steel shells filled with various components, the most important of which is air. This is known as reserve buoyancy. The air inside the ship is much lighter than water, allowing the ship to float. For a ship to float, the average density of the ship's total volume and everything inside it, including air, must be lower than the density of the same volume of water. When a ship is placed in water, it displaces an amount of water equal to its own weight. The closer the ship's total density is to the density of water, the more of the ship will be below the water's surface. If the ship's average density is greater than water, it will sink. When a ship sinks, it's because water has entered the ship, displacing air and making the ship's average density greater than water. One of the most famous ship disasters is the sinking of the RMS Titanic. The ship struck an iceberg off the coast of southern Newfoundland in April 1912. The iceberg tore several small holes in the ship's hull, allowing water to enter the front of the ship. As more water entered, the air was pushed out. However, buoyancy alone is not enough to explain why ships do not sink in rough seas. Other factors also play a crucial role in maintaining a ship's stability and balance, including the center of gravity and the center of buoyancy. The center of gravity is the point where the total weight of the ship is considered to be concentrated. The center of buoyancy is the point where the total buoyant force acting on the ship is considered to be concentrated. Ideally, these 2 points should be on the same vertical line, keeping the ship upright. However, in rough seas, external forces cause the ship to sway left and right, or forward and backward. These forces are called moments and tend to rotate the ship from its initial position. A moment is the result of the multiplication of force and distance from the pivot point. The greater the force or distance, the greater the moment. Moments acting on a ship can come from wind, waves, currents, or uneven cargo within the ship. These moments can cause the ship to tilt or even capsize if not balanced. To prevent this, a ship must have good stability. Stability is the ship's ability to return to its initial position after being disturbed by external moments. Stability is determined by the difference between the positions of the center of gravity and the center of buoyancy. The greater the difference between these points, the more stable the ship. The center of gravity and center of buoyancy can shift depending on the shape and distribution of the ship's mass. When a ship tilts due to external moments, the center of buoyancy shifts in the same direction as the tilt. This happens because the volume of water displaced by the ship also changes. The center of gravity can also shift if there is a change in the ship's cargo or passengers. When the center of buoyancy shifts, it creates a new buoyant force that tries to balance the external moment disturbing the ship. This new buoyant force acts as the new center of buoyancy, while gravity continues to act as the center of gravity. If the line connecting these points forms an angle with the vertical line, a restoring moment will turn the ship back to its initial position. This restoring moment must be greater than the external moment for the ship to remain stable. If the restoring moment is smaller or equal to the external moment, the ship will remain tilted or even capsize, a condition called instability. To design a stable ship, several key factors must be considered. An ideal hull shape with a large surface area but small volume, optimal mass distribution with a low and balanced center of gravity, the use of ballast to add weight and lower the center of gravity, the installation of stabilizers to reduce tilting, and the influence of ship speed, which can create hydrodynamic forces. These forces can make the ship more stable or less stable, depending on the direction and magnitude. By considering these factors, ship engineers and architects can design and build ships that are less likely to sink in rough seas. However, no ship is perfect, and there is no guarantee that a ship will never sink. Many factors cannot be predicted or controlled, such as weather, currents, ice, or collisions. Therefore, designing and building ship models is a time-consuming and complex process. Various potential errors and inaccuracies are assessed from the initial stages, with preventive measures and testing conducted at each step. This is why model ship testing is essential from the basic design stage of a ship before it is built. The importance of model ship testing can be explained by its name, where large objects like ships can be assessed on a miniature scale, allowing the visualization of the ship's behavior and other physical characteristics before the construction of the actual ship begins. Building these ship models requires hydrostatic calculations before the production stage, and completing the model with precision is crucial, as small errors can have a significant impact on the ship's design. High computing technology has simplified this process, allowing the creation of ship models in a manner similar to building the actual ship. Towing tanks are experimental facilities primarily used to calculate and solve ship hydrodynamic issues. These tanks resemble long pools, often with depths of up to 100 meters, and their width is usually determined by the width of the ship model itself. These narrow freshwater channels facilitate various experiments where the model must move a certain distance without significant cross movement. When testing a model, the ship model is placed in a towing tank, usually mounted on a carriage, a type of moving platform that travels along rails on the sides of the tank, moving simultaneously with the model. This carriage not only supports the model, but also serves as a base for recording equipment, computers, and other data collection systems. Researchers and observers can also ride on the carriage to watch the experiments directly. Model ship testing can also be conducted in facilities called wave basins. These test simulations are more realistic because these facilities create a testing environment for the model similar to the actual sea conditions experienced by ships. Physically, wave basins resemble towing tanks. They also have lengths that far exceed their width, and their depth is not very deep, although they can be deeper than simple towing tanks. Another interesting feature of wave basins is the deep pit in the middle of their length. The depth of this pit is quite significant and is made for technical reasons. The main idea is to create an ocean topography where there are various seabed depths ranging from shallow to around 10,000 feet or more. A unique feature of wave basins is the wave generator. This system generates waves with varying wavelengths, frequencies, and of course, heights. Now, the question is, how do we generate waves? The answer can be simple: with wind, by creating pressure variations and disturbances underwater or mechanically. Since it is difficult to create pressure variations and disturbances underwater artificially, the mechanical method is the best way. The mechanical method triggers hydraulic forces, which in turn create waves within the tank. These wave makers are essentially driven by electric motors. The model ship is towed at a certain speed while measuring various parameters, such as resistance, speed, and ship behavior. Advanced sensors are installed on the model to collect data during the tests. This data is then analyzed and used to make decisions regarding the ship's design. One critical aspect of the model ship testing is ensuring that the data obtained from the model can be applied to the actual ship. Therefore, it is essential to ensure that the model's scale and the actual ship are the same. This requires a deep understanding of similarity theory, which is a fundamental principle in fluid mechanics. Engineers use the results from model ship tests to make adjustments to the ship's design, fix shortcomings, and optimize the ship's performance. As a result, ships built based on tested designs will have better performance, be more efficient, and safer. The model ship testing process also allows engineers to test various scenarios and conditions that the ship may encounter at sea. For example, they can test how the ship will behave in bad weather, high waves, or even during a collision. By conducting these tests, engineers can identify potential problems and design solutions before the actual ship is built.